So as you know, these boot camps are designed to kind of give you preemptive knowledge before you learn it in class. And based on your pre-surveys, this is a completely brand new topic for everybody. So I will try to be as thorough and as, you know, well-paced as possible. So that way y'all can all definitely see how to do this stuff and understand what's going on. And of course, we're all adults here. If you need to leave at any point in time, go ahead and go. It's okay. This is an optional thing, so stay as long as you want. I am recording this service for your benefit as you can watch it at a later time. And I've been mentioning this in the previous boot camp, just to remind everybody that there's a bunch of formulas on this particular formula sheet that I personally find completely unnecessary. So in your lab manual, around page 56, depending on which version you have, you'll find a ton of formulas. And again, just to remind us, this very first one, you do not need it. Some professors have just been doing this job for a very, very long time, and they grew up with that formula. But it honestly is a waste of time and an unnecessary formula that you just don't need. And so the one you're going to hear me strongly advocate is this bottom one. Because this bottom one here, binom.dis.range, this one does everything the one above does and more. And it's just simpler to use. And so I'm going to give you the basic structure of how to use it now, because today is all about binom.dis.range or binomial distributions. And I'm going to show you how and we're going to also learn today when to use it, because you're going to find a couple of cases where we can't use it. So that's really important to know. So the first thing I'm going to tell you about is the basic structure of it. So the formula goes equals binom.dist.range. And what you need to learn or understand in Excel is .dis. Whenever we do anything .dis, that will always return or give the answer of a probability. So they say, what's the probability? Then they're asking you to use a .dis kind of situation. And that becomes really important in the next unit when they're asking you for different types of probabilities. And you'll find out we have norm.dis, binom.dis, t.dis. And so you'll have to know what kind of distribution we're dealing with. For this unit, it's only going to be binom.dis.range and norm.dis. But the .dist aspect of it tells Excel to give me a probability. So we're getting a probability in the binomial world. And we'll learn how to identify today what is a binomial. But let's talk about the actual formula now. The very first thing, which we'll go in more detail later, is going to always be our fixed trials. You'll often see us use n to represent that as a number. We'll say n equals 8, and that just means the fixed trials is 8. And so n is just our shorthand notation. It's going to write fixed trials every time. The next element will be our probability. We often call it the probability of success. It's simply the probability we care about. So the probability of smoking, the probability of going fishing, the probability of raining, whatever probability we're looking for, we call it the probability of success, which means that what you're looking for happens. And then we have probability of failure is obviously the opposite of that. And then we have the last part here, and there's usually two elements to it. And so the first one is mandatory. It's going to be some starting value. And the last one is an ending value. And you'll learn that this last option right here is optional. And so mainly the reason why it's optional is sometimes we're going to want to find the probability of an exact number. In which case there is no ending value because the ending value is the starting value. In which case I would do binom.dis.range, so BDR for short. And then we would do the fixed trial, the probability, and we only need to worry about this number, whatever number that is. And so I'm just going to call it number. And that's all you would need to do to enter in to get the probability of that exact number. But sometimes we care about the probability between numbers. Let's say we want to find the probability from 2 to 6, something like that. In this case, that starting and stopping property becomes very important. So the beginning is all the same, fixed trial, probability. But now we just need our start and our stop. And so we're starting at 2 and we're stopping at 6. And then you would hit enter and poof, there is your solution. And so that's the basic structure of the formula, but we're going to see it in action now so that we know how to use it more precisely and when we should be using it and when we shouldn't be using it. So I'm going to jump over here to tab number 0 now. So the first thing I really want to do is make the connection as to how these things are all actually the same. Because often people kind of gloss over that and you're just left to kind of connect the dots yourself. And I'm not a fan of doing that in education. So I am going to connect the dots for you and let you see the beautiful part, why we care, why are we spending time learning binomial when we do problems like you can see up here. And so we're going to see it first done by 0.5, is this probability given as 0.5. Then we're going to do the exact same question, and we're going to change that probability to 0.48. And you're going to see something really interesting, I hope interesting, happen when we change the probability from 0.5 to 0.48, making these a little wider for us. Oops, didn't mean to give that answer away. And so, yeah, let's do it. And one thing I want you to special note, just for those who are into the concept stuff, what's going on, you might notice that I changed the word from classical to generalized. And that's actually just a nice observation to note. And the reason why is classical probabilities assume that there's an equal split amongst your probability of each event. And so in this case, if boys have a 0.5 chance, so do girls, right? 50-50. And so if you have an equal split, like a dice, 1-6, 1-6, 1-6, 1-6, 1-6, everybody's 1/6, that's classical because they're all equally spaced out. But when the probability is not 50-50 or equally split, it is not called classical. And so we often call it generalized. Sometimes you'll call it empirical, all the same kind of thing. I am taught over in out of the country, so we use the word generalized. In America, they use the word empirical. Same idea. It just means that the probability is not equally split between each of the options. And so there is a slight little difference in vocabulary choice there. But let's actually look at these probabilities. And I'm going to show you a formal way, and then I'm going to remind us that the classical actually has a shortcut that allows this to happen. But let's do it the long way first. I know, you can hate me later for doing that. First off, we need to figure out what the possibilities are. We're going to make an outcome space. Outcome space doesn't list every single option. It allows you to kind of like nicely capture in a very short space what's happening. So let's zoom in a little bit. There we go. And so let's list in our possibilities. So we're trying to have 4 children. So we know that there are going to be 4 births. And the first place, if you consider gender as binary, boy or girl, essentially, there's 2 options. And then the second one is 2 options. Third child has 2 options. And the fourth child has 2 options. And by the multiplicative or counting principle, we can simply times these together and find out the total number of outcomes. And so essentially, I have 2 to the power of 4 because there's 4 2's there. Or 2 times 2 times 2 times 2, all the same thing, meaning there are 16 total ways we could list out. So if I had to, I could list out 16 different combinations of ways the gender could work out. So one possibility is that you have all boys. So I just write 4 B's in there. The next possibility is you have 3 boys, but then a girl. And we don't know what position that girl is. The girl could have been born last. She could have been born first. We're not sure. Then we could have 2 boys and 2 girls. And of course, 1 boy, 3 girls. And then finally, all girls. Now, what you'll notice in the first case, the all boys case, if I list out all the ways it can go, no matter how I rewrite that, it will always state B, 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 B. So the order never changes no matter how you rearrange it. So that's only one of the possible outcomes. There's only one way to write B, 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 B. If you rewrite the letters, it's still B, 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 B. It doesn't change. But for the girl one, the second case, notice with the girl at the last option, she could have been the third option, she could have been the second option, or she could have been the first option. So in this case, there are 4 ways to write it with 1 girl. So there's 4 possible outcomes with 1 girl involved. And so very similar by what we call symmetry, this third case, the one down here with one boy, I should say, that's also 4 options because the boy could have been first or second or third or fourth. So there's only 4 positions that that boy could be in. So there's only 4 possible outcomes. Then also by symmetry, if the first one is all boys and it has only one outcome, then all girls also has one outcome. So you'll notice I skipped this one in the middle because that one's actually often the hardest one to actually calculate and figure out how many options there are, which is why knowing how to calculate your total outcomes is very handy. If we know there are 16 total ways, then that means that all this needs to add up to 16. And of course, right now we have 1, 4, 4, 1, and 1 and 4 is 5. 4 and 1 is 5, so we know of 10 ways, which means that middle column, the one box we're missing, has to be 6. And so there are 6 possible ways to arrange 2 boys and 2 girls. Feel free to play around with it and try to see if you can find them all. But essentially, there are 6 total ways that you can list out 2 boys and 2 girls in any order. And now, if I wanted to be very formal about my probability calculation, you should remember from last week that what we're technically doing is we're going to take the probability of each characteristic. So in this case, boy has a 0.5 probability. And so it would be 0.5 times 0.5 times 0.5 times 0.5. And then we would worry about how many times that outcome can happen. And so 0.54 times 1. And again, I'm showing you the long way. I know there's a shortcut, and I'll show you the shortcut just for those who don't, see it right away, and that's cool. But for now, let's just do it the long way the first time. So, because it's going to matter for the next chart when we get there. We got 0.5 because there's all boys, so that's happening 4 times. So 0.5 to the 4th power. And how many outcomes, how many ways can we have this 0.5 to the 4th power? Only 1, so just times 1. I know times 1 doesn't do anything, but just for the practice. And so that's technically the relation of how many boys there are. And then the third case now we have, first we have to consider the probability of a girl. And if boys happen 0.5 of the time, then girls happen 0.5 of the time. And again, since these probabilities are exactly the same, we call this classical. And so now we have 0.5 happening 3 times because the boys is 0.5, right? The girl is also 0.5, and she's technically happening once. And again, just doing it the long way on purpose. And there's 4 possible outcomes of this, times 4. It can happen 4 different ways, so each one of those possibilities. And then, of course, by symmetry, if this happened 0.0625, we know the girls would also be the same calculation because they're also 0.5. So we can go ahead and snag that first answer down the bottom box and call it 0.0625. And the second one that was 0.25, because the boys and girls have the same probability, it will also be 0.25. Now we have a couple of options. We could just do the complement and 1 minus all that we know. Or let's do it directly. We could say 0.5 for the boys happens twice. And the girls is 0.5 happens twice. And this has 6 total outcomes. We get our probability. Now I mentioned that there was a shortcut, and this is the way that most of you did the first section that we talked about, because we're talking about classical, and that's really important. That's why it's important to be identified. Because we're talking about classical, these probabilities are the same thing as their outcome divided by the total. So had we done 1 divided by 16, because there's 1 outcome and 16 total outcomes, you get the same answer. 4 divided by 16, 6 divided by 16, that's not a 16. And then, of course, 4 divided by 16 again, and finally 1 divided by 16. And you'll see it's exactly the same. So then why did I waste my time doing it this complicated way? Well, because it won't always be classical. It won't always be where each characteristic has the same probability, in which case we can't do it that way. It's also showing us the formal way of doing it, so when we get to this problem, it won't look so different in approach. Just know that the probabilities are fundamentally the same when you do it that way. And now that we have this information, we could fill in this chart, at least for the first two boxes, pretty easily. The direct column, I should say, and the complement column. And yes, direct is another way of saying classical. So you have direct, classical, all the same kind of thing. Theoretical. So many ways to say the same words. So first off, we want the probability of at least one boy. So that means we want as lowest amount of one boy, and it can go up to all boys, which means 4 boys. And so if I want to do it directly, I would simply sum up from 1 to 4. So 1 boy up to 4 boys. That's at least 1 boy. If I want to do at least 2, okay, well, that means starting at 2 boys and up to 4 boys. That's at least 2. So starting at 2 boys on my chart and going up. Less than 2 boys. Well, what's less than 2? Well, 0 is definitely less than 2, and 1. Obviously, I can't do 2 because 2 is not less than 2. Now sum 0 boys and 1 boy. There's our probabilities doing it directly. But of course, there's an indirect method that we call the complement method. And remember that from last week, complement is just taking away what you don't want. So if I want 1 boy to 4 boys, what I don't want is 0 boys. And so I could just do 1 minus all girls. And notice the answer is exactly the same. Yeah, there's some extra zeros there. It's just Excel rounding for us. And so the complement of 2 boys to 4 boys, well, if 2 boys to 4 boys is these first 3 boxes, then I just want 1 boy or no boys. So we could just sum up 0 and 1 boy. That would be the complement of 2 boys or more. Oh, I forgot the 1 minus, didn't I? Complement is always 1 minus. I was getting worried there. There we go. Lastly, if what we want is 0 to 1 boys, then the complement is the sum of 2 or more, 2, 3, and 4 boys. Notice you can do it classically, you can do it by complement. It will always be the same solution. It's just a matter of how you want to do it. But the one major drawback of these kind of questions is in order to answer direct and complement for the most part, is that you're going to need some kind of fancy table like this. And I don't know about you, but that's not fun. Binomial allows you to get the same exact answer without needing to make a table. And so let's actually think about it. And let's actually talk about the elements that we just mentioned before. So remember the formula will be binom dot dist dot range. And the first thing we're going to call fixed trials. And what this actually is the number of events. Number of events. And then we have the probability of whatever event we're looking for. And of course, when we want to start counting and when we want to stop counting, where we don't need to stop if we want an exact number. We can just start and stop writing, essentially. So that's the basic structure. And so now let's think about what these elements are. Well, how many events are happening? We're birthing 4 children. So that represents our n right there. And then we need the probability of what we're talking about. And all these questions are talking about boys. And we happen to know the probability of a boy right there. So the probability of one of those events is 0.5. And the number of trials is 4. And then we just need to know where to start counting and where to stop counting. And guess what? We outlined that already. 1 is your start, 4 is your stop, 2 is your start, 4 is your stop, 0 is your start, and 1 is your stop. And so those are our starting and stopping elements. Notice all that information, the probability, the trials, the starting and stopping, none of that came from the table. So we don't need the table at all if you know that binom.dist.range is a thing. And so let's try it. Equals binom.dist.range. A births, 4 births. What's the probability of a boy? 0.5. Where do I want to start counting? 1, because of at least 1 boy. How high can it go up to? It can go up to 4 boys. If you have 1, that means at least. If I hit go, Boom, exact same probability, no table needed. Let's do it again. Gotta spell it right though. One nice little trick, by the way, if you see the list of words pop up, you can navigate to the second one and then just push tab and it will autofill the word for you so you don't have to write out the whole entire thing. Or you can just write it out, it doesn't matter. And of course, capitalization doesn't matter either. So 4 trials, 0.5 probability, 2 to 4, right? At least 2 boys. So start at 2, go to 4. And boom, same answer. Lastly, no, dot dist, dot range, 4 trials, probability of success is 0.5, 0 and 1, because start at 0, stop at 1, that's less than 2. Hit enter, same answer. So once again, doesn't matter which method you use, it just kind of depends on what information are you given. Are you given the fixed trials? Are you given the probability of success? Or are you given a table? If you're given a table, then you have to utilize one of the first 2 methods. If you're given a binomial situation, then binom.dist.range is definitely something to your advantage. To hit it home as why this is really, really important, because some people might say, well, if it's 0.5, James, it's actually not that hard to calculate. I could have easily come up with these outcomes and wrote the fractions. So I'm still kind of wasting my time learning a new formula. Let's go over to a harder problem. So again, notice this is not classical because we don't have a 50-50 split between boy and girl. They're not equally opportunity for probability. First off, let's recognize that if boys are 0.48, then girls have to be the complement of that, which is 1 minus 48, or in other words, 0.52. So we need both these probabilities, especially if I'm going to do it by the first 2 methods, the generalized and complement method, or the empirical and complement methods. Of course, the general possibilities is all the same. We know you're going to have 4 bursts of boys, 3 boys and a girl, 2 boys, 2 girls, 1 boy, 3 girls, or all girls. And so the number of outcomes will still be 1, 4, 6, or 1, just like we calculated a minute ago over here. If you arrive late, you can just go back in the video to see how I came up with that stuff. And we know there's still total 16 outcomes. So the real magic now is finding the probability of each of these events. So initially, we see that we have 0.48 4 times, and that happens only once with 1 outcome. Notice that is definitely not 1 out of 16. 1 out of 16 was that 0.0625 number. So we cannot utilize that classical approach of just taking the outcome divided by total outcome, that more formal idea. And so now if I do 3 boys, I would say equals, probability of a boy is 0.48, and there are 3 of them in this case, right? 3 boys, but there's also 1 girl, so 0.52, technically to the power of 1. I know you don't have to write it, but I like to write it just so I keep track of 3 boys, 1 girl. And there are 4 outcomes, right? 4 possible ways that can work out. And so that's the more formal calculation. I want to do it, by generalized or complement methods. So now we have to have 2 boys, 2 girls, so equals 0.48, 2 times 0.52, 2 times, because 2 boys, 2 girls. And there are 6 total outcomes, so times 6. And almost lastly, we have boys, 0.48, 1 times 0.52 to the 3, and that can happen 4 ways. We have 0.52 happening 4 ways, and technically times 1. Oops, I forgot my equal sign, didn't I? Cancel. Come in here, put equals, and there we go. So one nice check, if you recall, since this is a distribution, it shows how everything is distributed by probability. If we highlight our probabilities, it better add up to 1. And you can always check your work by highlighting your probabilities and looking down here. If the sum doesn't say 1, you did it wrong. And so the fact that it does add to 1 means that this, in fact, is the probability for what we're looking for. And the same idea if I would have highlighted here my distribution table and checked my sum does say 1, so we knew we did it right. That one I was less concerned about because the classical matched the more direct way of calculating it. Okay, so now the same exact concept, let's get these probabilities. So at least 1 boy means we're going to sum up starting at 1 boy and go more. We can say at least 2 boys, so we're going to sum up starting at 2 boys and go more. And then less two boys means sum up 0 and 1 boys. And there we have it. If I want to do complement, of course, it's 1 minus what you don't want. 1 boy means 1 or more, so take away 0 boys. Same solution. I can also do 1 minus the sum of everything that's not 2 boys or more, so 0 and 1 boy. And then lastly, I can complement out less than 2 boys by doing 1 minus the sum of everything that's not less than 2 boys. So everything that's 2 boys or more is not less than 2 boys. And again, notice, same solution. So you can do it, you can totally do it this way. I don't know about you, but finding these probabilities is not always fun to think about. Remembering your powers and all that stuff. That's where this formula on the right here is very, very, very beneficial. I still show you this way because sometimes, and you'll find out later on, sometimes the situation is not binomial, in which case you can't use that formula. It won't work. And we'll talk about situations where we have to do something like this and instead of using the binom.dis.range formula. But let's finish now. So binom.dis.range, there we go. Talking about 4 births. The probability in this case is of a boy, we're talking about boys in this situation, is 0.48. And at least 1 boy means start at 1 and go up to 4. Hit go, and same exact calculation. Second one, binom.dis.range. 4 total births, probability of a boy is 0.48, and I want at least 2 boys, so 2 up to 4. You can't have more than 4 boys because you're only having 4 births, right? So that's why that's the maximum. Again, same calculation. Lastly, binom.dis.range, 4 births, 0.48, and now we want less than 2 boys, so 0 and 1. There we go. So notice all 3 methods will always produce to you the same solution, assuming that the conditions for what binomial requires is met. And we'll talk about those conditions when we get to a question that asks you to prove the conditions. So I don't want to give that away just yet because that's extra thinking that we don't need to do just yet. Right now, I want us to practice using this formula, and then we'll talk about when we can't or can use it. Okay, long part, but hopefully you got to see the benefit of it and why it's also the same exact solution and why we can use it instead of the other more conventional methods. We could use a formula to save us some time, especially on those time exams. Okay, one more long drawn out one, and then we'll go a little faster through these. Read the question up here, and first try to see if you can pick out what information we know about the trials, the probability of success, and that kind of stuff. Okay, so this one's a little bit hidden in the question itself, but we're talking about over 3 days. And so that's being implied to be our trials. And so remember, just N means fixed trials. All that means is there an exact amount of days or objects that we're working with? We're working upon 3 objects, 3 days in this case. And so now what's the probability of rain? Do we know rain? Sure we do. Probability of rain is given right here. So that's considered our probability of success. It's success if it rains. There's a 20% chance it rains. And then we would just need to know starting and stopping points, and that's when you get into the questions down below. But again, just to hit home why we care about binom.dis.range so much, we're going to do this question the old way, the way we did it last week, and then we'll build in to show that they're saying the same thing. And then from there on out, we'll just stop using the old way and just keep doing binom.dis.range as good practice. So like before, but this time, instead of doing an outcome space, so notice outcome just listed in general terms what the possibilities are and how many there were. We're actually going to make a sample space. And so sample space shows each and every little possible arrangement. And so let's do it. So we'll first do the sample space, then we'll fill in our outcome space, and then we'll talk about these distribution tables and next. So our sample space, we have no rain or rain, where N is no rain, R is rain, and we're talking about 3 days. So one possibility is that it never rains. Never rain 2 days and then rain, which means that R can move to all positions. It can go no rain, rain, no rain, or rain, no rain, no rain. So the R was last, then it was second, and then it was first. What's the next possibility? Well, that was no rains, one rain. So the next possibility is 2 rains. So no rain and 2 rains. On the same trick I did with the R, where I move the R up slowly, I'm going to take the N and move it backwards slowly. So now we go rain, no rain, 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 none. So notice N was first, then it was second, then it was third. So that was no rain, no rains, 1 rain, 2 rain. So the last option is 3 rains. And I don't mean to hit page down, sorry about that. And so if we count how many objects that is 8 objects. And so the total outcome is 8. Right? You can just count down your list and see there's 8 of them there. But we could also confirm it. We know that the first day it could be no rain or rain, so 2 possibilities. Second day is no rain or rain. Third day is no rain or rain. So it's 8 possibilities. So yeah, it seems to match up. So what are the possibilities? The possibility is that it never rains, it rains once, it rains twice, or it always rains. So that's our outcome space, just listing out in general terms. We're not caring about order. Your sample space cares about order. So these 1-day rains are all considered different, while these obviously are not. They're just a group of them. All the 1-day rain possibilities, all the 2-day rain possibilities, and so forth. So in our sample space, how many times do we list never raining? Just once. Our sample space, how many times do we list raining once? 3 times. In our sample space, for 2 rains, we listed it 3 times. And always raining, we listed it 1 time. And so we could find the probability up here, but again, we're going to do it the long, boring way. And so let's find the probability of it never raining. We were told up top that 20% chance of rain, right? So let's make a note. If rain happens at a 20% chance rate, then never raining happens at an 80% chance rate, because 1 minus 20% is 80%. So we have never raining, so 20% happening 3 times in a row, or never raining but then raining, so 20% happening 2 times times, oops, I'm sorry. But never raining is 80%. 80% happening 3 times. Now, never raining is 80%, but there's 2 possibilities times raining, which is 1 possibility, according to that option. And technically you'd write 1. And there we go. And of course, the next one and the next one all have 2 no rains and 1 rain. So I can just copy and paste my calculation in there. Third one's different. We have an 80% chance of rain, and then 20% chance, no rain, and 20% chance of rain 2 times. So 80% 1 time for not raining, and 20% 2 times for raining. Oh, I forgot my little power there. So let's go back in and add my little power symbol, Shift-6. There we go. And so that's the probability of not raining and 2 days of rain. And let's just copy it, because these are also 2 days of rain and not rain. And then finally, raining 3 days in a row, 20% to the power of 3. And let's check our calculations. So we add these all up, and we look, we can see the sum, in fact, is 1. So we know we did the calculations correctly. And so technically we have 0.512 for the first box. The next one is 0.128. And so notice what I did is I would do that usual calculation, and that calculation is happening 3 times. That's why we would times it by 3 if you did it directly. We would have said, this calculation, and then I would have slapped on times 3 because there's 3 outcomes. All that we're actually doing is saying that it's going to be the same calculation 3 times. That's why we times it by 3. And we get 0.128 times 3. So I should have actually just said the sum of these 0.128s. And then I can say the sum of these 0.032s, because we're all 2 days of rain and 1 day of no rain. And then finally, we just need that last calculation. And so there is my outcome space if I care. I have my individual values. And they do still add up to 1. So this represents the sample space with each of their unique probabilities. But because a lot of these have the same calculation, we can shortcut it by saying times 3 and times 3, because there's 3 of them with the same exact probability because of the number of repeated sample spaces. By just moving position, it's still the same number of rain days and not rain days. So if we want to make a distribution table, what we always do is you start at the fixed trial worst case, which means it never happens. And then you always count down to the max case. So it'll always be 0 up to the total fixed trial. So in this case, we're talking about 3 total days. So you start at 0 and just go 1, 2, 3 to your maximum amount. And then we want to put the probability of each of these happening. So what's the probability that it never rains, rains once, rains twice, rains 3 times? And so, of course, we can look over our table on the left here and say, well, it never rains 512. It rains once, that 1 second case, 0.384. It rains twice, 0.096. And it rains all 3 days, 0.08. And technically, that's our binomial distribution table. So notice your outcome space actually is the same thing as a binomial distribution table. So we don't necessarily need this if we're going to make this one anyways. Secondly, second thing you might want to notice is that they're only going to be the same thing if it's in fact binomial. And we'll learn, I think, on the next question exactly how to determine if it's binomial. If they're not binomial, then of course you can't do this in the first place. And these probabilities will be done a different way. Mainly the ways you learned last week, which is why you learned the long way. Lastly, let's actually do the binomial distribution by formula, so we don't have to make the sample space or the outcome space. We can just jump right into it. And so we know how to do this now. Binom.dist.range. For trials, how many days of rain are we considering? We're considering 3 days of rain. What's the probability of rain? 20%. And notice you don't need to worry about converting decimals. Just write it as a percent. Write it as they give it to you. Now here's the only thing. We don't have a range. We only want that 0. We only want that 1. We only want that 2, all separate. So that means it's not a range. It's just a single value. When that happens, you just need to click on the 1 value or type the 1 value in. I prefer to click because now we can drag it down and get all the solutions really, really fast. So if I close it and hit enter, that's my calculation. Notice it's the same answer. No table needed. And because we wrote a formula and we used a cell reference, I can now go back to it and just grab this little corner and drag it down and get all my calculations done instantly. A lot faster and no need to blab on like I did for all that time, right? And so again, binom.dist.range, the fixed trial, the probability, and because you want an exact value, we want it to be equal, we just need to click on or type in the 1 value that we need. If you had a range, you'd do the starting and stopping number. But this is it. This is a binomial distribution table. It tells the reader when it's 0, it tells the reader when it's 1, it tells the reader when it's 2, it tells the reader when it's 3. That's all it does. And if for some reason you need a cumulative distribution table, same thing from the previous unit. If I want the cumulative of x, we would just utilize what you learned in the previous part, histograms. The first row is always the same, and the next one adds the top to the side, right? That's how we did cumulative last time. We just add them as you go down. And so we're going to add this 0.512 to the 0.384, and we'll just take it, cancel, and we'll just take it all the way down, and there's your cumulative. And don't freak out, it's just because the cells are so small that they're rounding for us. If we widen the cells or go to home and add decimal positions, of course they will undo that rounding. And so we can totally do a cumulative probability distribution table by just adding as we go down. So 0.512 is always the same, then you add 384, then you add 0.96, and then you add 0.008. So there's your cumulative probabilities if you needed it. Sometimes I'll ask you for a cumulative binomial distribution table, in which case you add that group there. Okay, all that. Now let's actually answer the questions, right? So what's the probability that it rains all 3 days? That's easy enough. We just look at our chart. 3 days, 0.008. That it will never rain over the 3 days. That means raining 0 times, 0.512. Lastly, rains at least 1 day. Well, that's 1 or more. So I can either do the complement, I can say 1 minus never raining, or I can, of course, just add up the ones I care about. I can add those 3 values. But that's how you would utilize a chart like we just did to get our solutions. Now, the next few questions aren't going to ask us for a chart right away, and we're going to do it directly from the formula. I promise you it gets faster. I just wanted to build up and show you why this is all actually the same thing, but why this method is going to be so amazing for you. Because when we get to questions like this one, where you got 500 items, which means 2 times 2 times 2 times 2, 500 times, you're not going to be able to create a sample space for that. 2 times 2 times 2 times 2 times 2 by itself is already 32. When you add more 2's than that, you're going to have an astronomical number. And so you're not going to be able to make a sample space and find the probabilities like we did on the first 2 questions. It just so happened that this is a small number of items, so it's easy to do it by hand. Soon we're going to get the problems that you can't easily do it by hand. All right, take a second, start reading this question and see if you can hypothesize how I know this question would be binomial. If you can tell by the first question right here, we're showing that it is binomial. We're showing that it is binomial, so we know it's binomial, but you have to be able to justify why it's binomial. And there are 3, arguably 4 criteria that we look at to determine if it's binomial. Think for a second, why or what about it probably makes it that way? Well, as the name itself implies, we're talking about the binomial criteria. Bi, right? It means that we got to have 2, or I should say only 2 outcomes. And generally, we like to phrase them in terms of yes or no. So if you can phrase it in terms of yes or no outcomes only, not yes, no, maybe, then we would consider that as the first condition. There's more. The second condition is that we need to have a discrete, finite, fixed trial. So what does that mean? It means that we need to work on countable objects that have a definite number. So we can't do things that are continuous. Like we can't use this on weights because you have decimal values and that kind of stuff, and you can't count from an interval of values of numbers. So those kind of situations we can't use binomial for. It has to be like 5 soup cans or 100 people, something that you can definitely count, and it has to have an n number. We can't do infinite cases. There are probability calculation techniques out there that are non-binomial for the infinite case or non-discrete case. In fact, the next one we're going to learn next week, called normal, involves those exact things. It's the opposite kind of situation. Third one is we must have a probability of success, and it must be the same for each item. I usually say people, but these aren't always going to be people. So whatever the item is. So the probability has to be the same opportunity. So previously, we're talking about 0.48 boys, and that means that any boy would have had a 0.48 chance. Okay? And so one boy would not have a different chance than another boy. If they did not have the same probability, we don't have a probability of success. It doesn't work. The last one is the fixed trials must be independent. And this is the big one that often causes us to have a non-binomial situation. So this is probably one of the most important ones. That one and the first one, to be honest, are usually going to be the ones that are the most obvious cases where it won't work. And so fixed trials must be independent means that for each trial, so in the previous question, we had four births, right? In the first case, we had two possibilities, then we had two possibilities, we had two possibilities, we had two possibilities. Notice these numbers were always the same. That's what I'm referring to when I say that. Each birth did not change the total amount. On the other hand, if we're playing like a card game and we had 52 cards originally, then we took a card out and we have 51, and then we had 50, and then we had 49. These numbers, the total amount of cards, are changing. So that's not going to work in terms of being binomial because you cannot have the base changing. And so any case essentially that involves no replacement will fail this case. So this assumes essentially replacement. And something that people often confuse with replacement is they often think of it as putting something back. When we say replacement, what we're actually saying is the number never changes. Now, of course, when we use the word colloquially, like if I'm talking about physically playing a game and I put the card back, that is a physical version of replacement because you are replacing it back in there. But what it more generally just means is that the total amount of objects you're working with, the total possible outcomes never changes. When we're talking about birthing of kids, for example, when the first boy is born, he's not replaced back into the mother to birth the second child. So there's not actual replacement, but the opportunity for the second child is back to boy or girl. And so we're talking about the opportunity of replacement, right? And what are the possible outcomes for each individual trial? And so each one of these spaces represents a trial, and every one is always going to be two if we're talking about births. So that's assuming replacement. And so if it's not replacing, then of course it's not a fixed trial. I'll just leave that there. And so we have to have these four conditions must be present in order to use binomial formulas. And that's great because when binomial formulas happen, there's a lot of shortcuts we get to take instead of doing that long table method. And so let's see this now. So read this and see if you can verify that these four things exist. That is the yes or no situation. We have a discrete, finite, fixed trial. We have the probability success. We're going to assume it's the same for everybody. And the fixed trials appear to be independent. Because it says show that, we know that it has to be true. We just have to find a way to shoehorn it in. So whenever you see a question that says show that, they're telling you that in fact it is binom.dis.range kind of situation. So let's see. Let's start with the obvious. We have 7 objects, and they are articles. So these are definitely discrete objects. This is why in the first unit you learn how to identify discrete things. So we have the fixed trial is discrete and fixed, which just means finite. There's not infinitely many articles, right? And that number is 7. And that's going to help us later on. That's our N. That's our sample size, aka our trial size. Okay. Do we have a probability of success? Well, first off, we need to identify what we're looking for. We're looking for this X thing, which is let X be the number of articles that contain no factual content. Do we have a probability of no factual content? Yeah, 11.6 has no factual content. So 11.6 is our probability of success. And now we just have to verify that it's the same for each item. Can we reasonably assume that 11.6 applies to all articles? Based on their study, at least. And yes, unless there's evidence, unless they tell you explicitly otherwise, we assume that it does. We assume this applies to all articles. If they said, well, 11.6% applies to, science articles and 20% applies to, I don't know, news articles and that kind of stuff, then we don't have one consistent probability and that would fail that condition. But because we have one probability that seems to apply to any kind of article, then it doesn't matter what kind of articles we select, we assume that applies to it. So we are good with the probability of success. So we have a discrete finite situation. We got a probability that seems to apply to all articles, one big global probability. Now we need to worry about the yes or no situation. But what would yes or no be? Yes is always whatever the x is defined as. And so x is defined as the number of articles of no factual content. So yes means the article has no factual content. And so yes, I am saying that yes means no. In statistics, that's going to happen a lot. It just yes is whatever statement we're looking at. We're looking at no factual content. So yes, it means that the article has no factual content. And so what does no mean? No is the opposite. The article has factual content. And yes, we do that a lot in statistics. So sometimes yes will mean that the person died and no will mean the person did not die. So we just do that a lot. So whatever they define your X to be, that is always your yes. So this is my yes statement. And so now we have a yes or no situation. Great. We have fixed trials, we have probability of success. We just have to make sure that it's reasonable to assume that the I'm sorry about that. I keep pushing the wrong button. I'm using a different computer today. But we need to make sure it's reasonable to assume this last case down here. Hold on, my screen stopped scrolling for some reason. Scroll. There we go. That the fixed trials must be independent. That each event must have the same number of possible outcomes. Well, let's think about it. We're going to select 7 articles. And we're trying to assess the first situation, right? And the first article could have factual content or it may not have factual content. So there's 2 possibilities. The next one also has 2 possibilities, 2 possibilities, 2 possibilities. In other words, this one having factual content or not factual content doesn't change that possible amount of factual content. Either it does or doesn't have it. So in this case, there's no evidence to prove that this first answer is influencing the next answer. In other words, they're independent of each other. And so it appears independent. The main thing you look for to determine if it's not independent is there any evidence of not replacing? And there's no mention of that. So we're going to assume that each of these are either yes or no situations, which we already kind of established here. That's why it's 3 arguing before, because essentially if you're establishing yes or no, do you really need to verify the 2-2-2-2-2 case? And there is some really weird exceptions where it does, which is why people often call there a 4th kind of measure or 4th criteria. Because you can't have a yes or no case where it's not always going to be the same number. It's some weird cases where it happens. And so we always just kind of talk to it. But for the most part, that fixed trial independent check, we assume it's true unless we have proof otherwise. And so you would just say appears independent, unless you see some kind of obvious indication that it's not, like that whole replacing idea. Okay, so now we want to construct our probability distribution. In this case, since we know it's binomial, we would call it a binomial distribution. Hint binom.dis.range, right? And we're going to label everything on our table. And I took some liberties already. You always identify what your x is, and then next to it, you always write p of x. And so according to the question, x was the number of articles that contain no factual content. And remember, our chart always starts off with the worst case. That means that there are 0 articles with no factual content. In my opinion, it's the best case, but we're just assuming based on terms of x. And then we count up to the highest fixed trial, which we know is 7 from the question. So 1, 2, 3, 4, 5, 6, and 7. So now we just need to find the probability of each of those events. But the cool thing about Excel, when you write your formula one time, we can quickly get everything we need to get. So we would say binom.dist.range. Total trials is 7. Probability was told to be 11.6. We want just that number, just that 0. So click on the 0 box. And if you scoot to the right, it will scoot your formula over usually. It's not doing it this time. Of course, we can always just stretch. Make it a little wider so we can all see it. Just stretch the cell. Binom.dist.range. Again, we had 7 trials, 11.6%. And then just that 0 because we wanted it to be only that one calculation. hit enter, and there's your first calculation. And then we can drag it down. Now, one thing I want to point out to y'all, because sometimes students see an E in their number, and they think that it means error or something like that. That's actually scientific notation. That's Excel being lazy. What that means is there's actually about 6 or 7 decimal zeros in front of that number. Actually 6, but if you count the one in front of the decimal, it's also 7. So in other words, we could say this is 1, 2, 3, 4, 5, 6, 7, and then 2, 8, 2, 6, 2, 2. That's actually the number it's showing us. Excel just doesn't want to write all those zeros. And so it quickly changes it into scientific notation by essentially truncating off those zeros, but telling you there's actually a bunch of zeros in front. So if I hit enter, notice Excel just changes it. Excel's like, I don't want to write all those zeros. And so don't freak out when you see that. That just means it's a very tiny, tiny, tiny number. It just means there's a lot of zeros in front of it. In fact, you can say there's actually technically, 6 zeros in front of it, but behind the decimal, 7 if you count the one in front of the decimal. So likewise, if I write 0, point, and then 4 more zeros, 1, 2, 3, 4, I can then write that number, and we can see this is the exact same calculation. Excel just doesn't want to write all those zeros. That's all it is. So don't freak out if you see E in there. That's okay. It's just a very tiny, tiny number. It's very unlikely you'll find 7 articles that have no factual content. Almost 0, right? Let's check our probability distribution. We're going to highlight them all, look at our sum, and see it says 1, which is a beautiful sight. It means you did it right. Okay. So we have our distribution done. Great. At least one of the 7 articles. Well, we have a table, so let's just use our table. At least one means you're going to sum from 1 and on down, right? 1 all the way down. Or, of course, we could have done the complement in 1 minus the 0 case. Doesn't matter which way you do it. Found the probability between 1 and 3. And when we say between, we generally mean inclusive, between starting at 1 and going to 3. We don't literally mean just 2. We want 1, 2, and 3. So sum, right, sum, James. There we go. From 1 to 3. So starting at 1, going to 3. It is. So notice it's a higher probability of getting something from at least 1 than it is from just 1 to 3, but they're almost the same. We want to compare probabilities. Always the higher the probability, the higher it is. But there we have it, y'all. So let's actually get into some more number crunching. We'll go a little faster because the formula doesn't ever change. So try to see if you can pick out the elements to make this a binomial distribution, because if it's binomial, we get to utilize that formula. $25 was our selection. So there is our fixed trial. This probability applies to all resumes, so that's our probability of success. Great. And talking about lying, so yes, it contains lies, no lies. Right, so that's how we're talking about it, because we're defining this as lying. All these are about lying. So that refers to our yes component, and no is not lying. Okay, and can we randomly assume that each condition is independent of the next? Because there's no evidence otherwise, we're going to assume independence. We always assume that unless we have proof otherwise. It'll have to be rather explicit. So since we have this, we can utilize our formula and save some time. So binom.dist.range. Fixed trials was 25. The probability was 85%. And 20 to 24. 20 to 24. Here we go. That's it. It literally tells you what numbers to put there. 20 was the first one, 24 second one, because it says 20 to 24. Okay, now we want to know expected value. And if you were here last week, and standard deviation, you might remember for discrete distributions that the expected value formula was the summation of x times p of x. And we had this other one called n times p, and that's for everything else. And then for the standard deviation, the only formula we had talked about was the discrete distribution one, so I'm going to call it DD for discrete distribution. And that was this monstrosity of the square root of x minus the average squared times p of x, all added up. And binomial requires it to be discrete, right? So that means the binomial distribution actually is a discrete distribution. So these formulas hold for it. So let's do them real quick. We're going to go through a little fast because we actually have the general, I think, idea of all this. Let's see, x times p of x. And so we want all of our trials starting at 0. And we know it needs to go all the way down to the fixed trial amount of 25. So add 1 to it. Take this all the way down to 25. 21, 22, 23, 24, 25. And all I did, by the way, was say the cell above it plus 1, and then just dragged it down until I got 25. So it automatically adds for me. And then we want this binom formula. Binom.dist.range. Total fixed trials was 25. Probability I already forgot was 85%. And we want only the value of that 0. Close it, hit enter, and we get our first calculation. So that number, of course, has 21 zeros, 0.20 zeros, then 25. That's very small, right? So if I click on it, you could drag it down, but there's actually another nice little shortcut. If you go to the corner and double click really fast, it will also drag it down for you and do all those calculations. If you have a tablet, that kind of thing, you're stuck dragging because I don't think you can double click it. Could be wrong, but to my knowledge, you got to drag it down on tablets. And now if we check our sum total, we see it does say 1. So there is our binomial distribution table. Obviously, to do it properly, I would say x equals applicants' resumes that have lies, that kind of stuff. But we're just kind of getting a rough estimate because we only care about getting this expected value. So we need x times p of x. And you know me, I'm going to write little facts here so I know what I did if I ever go back over this. So x times p of x. Get my first calculation. Then what do I need? I need to find the sum of that calculation. So we're going to say equals sum x times p of x column. So just click on the W. That way it adds up all those calculations for us. Hit enter. And now we're ready. We're going to click on our 0. We're going to double click this corner really fast so it runs and does all those calculations for us. And notice the formula automatically updates. It gives us our sum, which in this case is actually the expected value. So just in case you forgot, expected value for discrete distributions is the same thing as the mean, which is why I'm using that same formula as the mean formula. They do the same calculation. So our expected value is 21.25, which again is the same thing as saying the mean. Okay, well that's not too terrible because we have Excel doing this quick calculation for us. Let's go ahead and get our standard deviation, this monstrosity. So we know we're going to need some notes here. X minus the mean. X minus the mean squared. And we'll do x minus the mean squared. So I'm just building it up in building blocks here, times p of x. And then finally, we could find the sum, which is the variance, and then our standard deviation, which is the square root of the variance. Double click some of these cells to expand them out appropriately. So x minus the mean, this x value, the 0, minus my mean, I don't want that to change, so 21.25. Okay, there's my first calculation. And then we're going to square that calculation, so equals, click on the negative 21.25 squared. And then we're going to do that calculation times p of x. So equals this calculation times p of x, that one way over there. So that 451.56 number times the p of x number. And then like before, we want to find the sum of all of our calculations in AA. That's your variance. And then finally, the square root of your variance is your standard deviation. Okay, but these first few columns, from Y to AA, need to go all the way down. So if you highlight all three, double click your corner, poof, it does all those calculations for you. Excel's a beautiful tool. So again, I only had to do those calculations one time. Then you just double click that corner really fast and it will drag it down. If I didn't have that option, I could just drag it down manually and it would still produce the same results. And notice it updates fully, and there's my variance and there's my deviation. But do you remember where I told you earlier? I told you that binomials, when it's binomial, has a beautiful shortcut. And that's 100% true for these calculations too. I just wanted to show you, because binomial is a discrete distribution, these formulas do hold. It just depends on how the data is presented. If you can justify and you can show that these things exist and all this stuff is true, then you get to utilize the shortcut. Namely, binomial distributions, that's not a B, is it? Binomial distributions actually can utilize this calculation for expected value. And they also have a nice shortcut for standard deviation. They use the square root of n times p times q, where q is nothing more than 1 minus the p. It's the complement of p, your probability of success. So n would be our 25, and p is 85%. So don't get mad at me. I just want to show you that it's in fact the same thing, so you see all the connections. But our expected value could have also been found as our total trial size times the probability of success. Look at that, 2125, 2125, the exact same answer. The standard deviation then would be the square root of n, which is 25, times p, which is 85%, times q, which is not p, so times 15%. N minus p times q. So if I just did 1 minus 85%, I'd find it's 15%. Hit go. 1.785, and what does this say? 1.785. It's the same number. So, yay. You can identify that we're dealing with a binomial distribution. We have shortcuts. Binomials can be done by NP and the square root of NPQ for your expected value and your standard deviation. You only utilize these calculations when you deal with a discrete distribution that does not meet those above conditions. So even if you have a binomial situation, if you cannot find your n or your p, you can't use the shortcut. You have to do it the long way, which is why it's still important to know how to do it the long way, because sometimes they'll give you a binomial situation, but they won't give you the probability of success, in which case you have no choice but to utilize this approach. Okay. For part D, we're trying to determine if something is significant. Significant is identified as the probability of an extreme is less than 0.05. If this is the case, then we say, yes, it is significant. And so what do I mean by extreme? Well, essentially, if you remember from the previous unit, when we look at a distribution, let's assume like a nice little mountain-shaped one here. If we have a value, so we have our center, right? Our center measurement, which we'll just call the mean. And we have some kind of observation on this side. I just arbitrarily picked a side. When we talk about extreme, we're talking about the smaller side. So from X's perspective, we have this part here in yellow, and I got the other side of it in blue. Since we're looking for the probability to be very, very small to be significant, because when it's small, that means it's unusual, and therefore it's something that you should look into. It's significant. So when we're looking for the smaller side, we want to find the probability of whichever side is the smaller calculation. So in this example, we would find the probability that x is less than some number. Or on the other hand, if x was on the other side, so there's our middle, and then x is on this side, we would care about our observation being on the right. And so we would look at the probability of x being greater than the number. And if that probability is small, if it's less than 0.05, we call it significant. If it's not less than 0.05, it's not significant. It's not unusual. So we're looking to find out, is the probability of 15 resumes containing lies, is that significant? And so what we have to first think about is, what is the center of our distribution? Well, our center is our expected value, aka our mean. And we already calculate that. We expect to be on average 21.25 to be the most, the midpoint of where all this stuff happens. And so now we're looking at 15 resumes. Well, 15, is that smaller or bigger than 21.25? It's smaller. It's over here. So we're actually looking to find the probability of being less than 15. So what we want to know then is the probability of our measurements less than or equal to, technically equal to, I should add equal to, 15. Is that smaller than 0.05? If that probability is smaller than 0.05, then we say it's significant. It's unusually low because it's smaller than 21.25. If it's bigger than 0.05, then it's not unusual. It's normal to see that many values. So let's do it. And let's use the formula this time. So binom.dist.rate. Total trials is 25. The probability is given as 85%. Terrible memory here. 85%. And I want everything less than or equal to 15. So the smallest it can possibly be is 0, and it can go up to 50. So 25, 85%, 0 to 15. The probability of finding that many resumes is 0.002. Is that less than 0.05? Simple decimal lines up, 0, 5. So we're comparing 5 and 0. We can see that it is way smaller. And so, yes, this is significant. Significant. I don't spell well, forgive me. Yes, this is significant. In fact, we can say it's significantly low because 15 is smaller than 21.25. Which means if you get 25 resumes and you found only 15 of them had lies on it, that would be very unusual. You would expect much more, closer to 21 resumes out of 25 to have lies in them. In other words, practically everybody lies on their resume. But yes, that's what we'd find. Of course, I could have used my table. I could have simply started at 15, added all the way up to 0, and you would see that this calculation of 0.00214 is the same calculation I was getting here, 0.002. If I stretch it out, you'd see 14 in the next decimals. But ultimately, it's considered significantly low because 15 is smaller than 21.25, and the probability of this happening is very unlikely. Anything bigger than 0.05 we consider likely or possible. Less than 0.05 is extremely unlikely. Not impossible because it has a probability, just unlikely. There we go. We'll get some more of this is it significant in a little bit. The same, so let's go a little faster. 41% of Americans in general, so that sounds like our probability of success. And it seems to apply to all Americans, so it seems to be uniformly applied. We have a fixed trial that's discrete. We have objects of people, so that makes sense. And we either have yes, you have brown eyes, or no, you don't have brown eyes. And because we have no evidence otherwise, we are going to assume that they are in fact independent. We always assume that unless you see otherwise. So let's get into it. It says make a histogram. Okay, well, that means we're going to need to make one of those actual, sorry about that, back. Make one of those distributions. So x of x. Just verifying you can still see my screen. Okay. And so we want for 21 objects, so starting at 0. And then we're going to add 1 each time going down. So that's 1, 2, 3, 4, 5, all the way down till 21. Ooh, further. Oh, way too far. Yeah. Highlight back and delete. There we go. Okay. Now we need our probabilities. So let's see. Binom.dist.range. Trials was 21. Probability of having brown eyes is 41%. And we just care about this one calculation, so just that 0. Hit enter. Take it all the way down by double-clicking really fast. Verifying that the sum says 1, so we know we did it right. There is our distribution table, but they don't want a distribution table, right? They asked us for our histogram. But we know what to do. We got our data, so let's go up here to insert. And bar graph. Pick the first option. And there's our distribution. So let's remove some things on it. Let's take our gaps away. Lots of ways to do this. You can also just go to quick layout number 8, right? And we have a histogram. So some things we can note about it. We have a peak in the center, tail on the right, tail on the left. So you could argue that this is bell-shaped. You could argue that the tail on the right here is a little longer. So you could say with a slight right skew. Lots of different things you can talk to about this. So it's not symmetric because the right side's longer than the left side, right? 22 to 12 is about 10 spaces. 1 to 7 is about 7 or 6 spaces. So it's a little bit more longer on the right, but lots of ways you can describe this. But that's essentially what they want to see, is some kind of histogram. And so, well, let me move the picture, the words when I move the picture out of the way. So I'm just going to delete the words. And now let's move this out of the way so we can continue on. And then, of course, you know how to actually properly label it. You change your titles at the bottom, all that fun stuff. So I won't drag on because that's from test 1 material, and we are all good with that, I hope. And let's move on. So the probability that exactly 10 have brown eyes. So let's just do it by the formula so we don't have to keep going back to that chart. If I want exactly 10 brown eyes, binom.dist.range. You know we're talking about 41%. So 41%. No, total trials first, which is 21. Then 41%. And then you want exactly that number. You want just that number, so we're going to say 10. No range. And that's it. Now the next one says at least 10, which we know by now. At least means that number or more. We have, again, 21, 41, back up, 41 total. That's 41%. 21, my memory, is 21 people, 41%. And now we want at least 10. So the lowest it can be is 10. The most it can be is 21. And there we go. So 21 for the total amount of people possible. The fixed trial. The probability of it happening. The lowest amount, the most amount you can get. And there is our calculation. Now it says less than 9. Okay. So we can actually not bleed over to those columns. Let's make some more space here. There we go. So less than 9. Binom.dist.range. 21 people, probability was 41% less than 9. So what's the lowest it could possibly be? It's less than 9. 0. What's the most it can be? Not 9, because less than 9 can't be 9, because 9 is not less than 9, so 8. So 0 to 8. Remember, these are discrete objects, so we don't need to worry about decimals like 8.9, 8.8, just whole numbers only. But there's our calculation. At most 8. So the most you can go to is 8, but you can always go smaller. So binom.dis.range, 21 objects, 41%, at most 8, so as low as 0, but up to 8. It happens to be the same calculation because they're both going 0 to 8, and that's okay. There's just different ways of saying the same thing. More than 7, okay. Binom.dist.range, 21 objects, 41%, more than 7, so the smallest it can be that's more than 7 is 8. The most it can be that's more than 7 is 21, right? Up to the maximum amount. And there we have it. At least 4, but no more than 8. So let's think about this now. The lowest is 4, but you can't go past 8. So we're getting a range. We're starting at 4 and we're going up to 8. Okay, that's easy enough. Binom.dis.range, 21 objects, 41%. The lowest is 4, and the most is 8. So notice these binomial calculations aren't that bad. You just have to verify that it is in fact binomial to use them. Mean and standard deviation. So now remember, mean is NP for binomials. We get this wonderful shortcut, and deviation is NPQ. So our NP case is, stop doing that. Our NP, our N was 21, right? And our P is 41%. That's where our values are coming from. So let's do it right here. NP, so our expected value, always like notes, is 21 times 41%. Do the same calculation if you did the long way. And our standard deviation is the square roots of N times. One thing to note is it may not always be obvious what Q is. It may be like a hard calculation. You may not have time to sit there and worry about it. Well, within this, you can actually go ahead and just write the complement statement. So we could say times, parentheses, 1 minus the P. Or Q is nothing more than 1 minus P. And so in doing this statement, I have my N, my P, and 1 minus P is Q. So you could also do that if you don't want to manually calculate what Q is. And just make Excel do the heavy work for you. So there's your standard deviation. Okay. Now we're talking about a range of values. This is getting at what's known as the usual range. And it goes back to what we learned in the previous chapter. The usual range is defined as the center minus 2 standard deviations and the center plus 2 standard deviations. Then after we get that calculation, because remember this is like the whole z-score thing, minus 2z plus 2z. And after we get that calculation, remember that we're dealing with discrete objects. And so we'll need to convert them into discrete situations. So let's actually get our usual range then. It'll be the center, which is your expected value. That's where we're assuming the center to be, right? So we know that to be that 8.61 number. So I'm going to click equals, and then click on the 861. And you know, minus 2 times the standard deviation. That's my lower exact value of the center or the usual range. So now if I do my center, my expected value, plus 2 times my standard deviation, I get the upper value of the usual range. And so these are the exact values, but notice that these are not discrete values. So they don't make sense in terms of how many people or how many things that might meet the situation. We're talking about brown eyes. You would never find 4.1 and 13.1 people with brown eyes. We're talking about do you or don't you have brown eyes. So one thing I like to remind students of so you can figure out where these numbers are is what we're saying is that 4.102 and 13.112 are the most extreme you can possibly go. And so any number out here is too small. Any number out here is too big. So we want the first whole number within this range. So notice that I can't say, well, I'm going to round this to 4 because 4 is in the too small range. We can only ever go inwards in our range. So what's the first number after 4.1? That's a whole number. That number is 5. So 4 people is way too small because it's smaller than 4.102. And so the first number that's not smaller than 4.102 is 5. And the first number down from 13.112, that's 13. And so our usual range, our range of values that would be considered usual or not significant, is 5 to 13. And so anything from 5 to 13 would be expected or normal. So if you go out and talk to 21 people, you expect 5 to 13 of them to have brown eyes. That would be a normal encounter, nothing unusual going on. If for some reason you found 4 people, 2 people, or 17 people with brown eyes when you go out and talk to them, that's something unusual about that group of people. Maybe they're a community that just all have brown eyes or something like that. It's not the overall averaged value. So there's something different about that group of people from our standard value people. So this is just telling us what we would normally expect. Because obviously there's variation in groups. If you go talk to 25 people, sometimes 10 of them, sometimes 11 of them should have brown eyes. It can vary. But anything from 5 to 13 is what we would consider expected or not unusual, significant, not significant. Anything outside of that is extremely high or low compared to what we expect based on our data, based on what we know about how often people have brown eyes in America. And so that's the usual range. You just go 2 deviations both directions, then turn them into discrete numbers by going inwards towards each other. Okay. I know it's getting close to time, so if you got to go, I understand. I will stay and continue recording until this is all said and done. And so let's keep it going. So now, of course, let's get our calculations going. I'm going to go a little faster because we've been doing the same thing over and over and over now, right? So does this count as binomial? Well, that means we got to find our stuff. Do we have fixed trials that are discrete? Absolutely. There's 500 of them. Do we have a probability of success that applies to the whole group fairly? Absolutely. This applies to all Americans. It applies to the whole population of Americans. Do we have a yes or no situation? Well, what's X being defined as? Are you a smoker? So yes. Yes, you smoke. No, you don't. And we always assume independence unless there's an indication of not independence. So no one mentioning about non-replacement, so we are good with our fixed trials being independent. Okay. So let's do it now. We got binom.dis.range, 500 total people. Probability is 18.1%. And we want only that number when exactly 80. So just write 80 and call it a day. And now to save some time, since we know that the fixed trials and the probability of success will never change, I'm going to highlight that part. And I'm going to copy it. So I can just paste that in each time and quickly get the calculations a little faster. The only part that will change is where I start and stop counting. So hit enter. Here's my first probability. Now if I double click in the cell, I can then paste. And now I already have the first part written. At most 80. That means it can go as low as 0, and the most you can have is 80. And there's my next calculation, very, very fast. At least 100, double click, paste, at least 100, so the lowest it can be is 100, and I can go up to the maximum, 500. So if you have 500 people, The probability that 100 or more smoke is 0.148. Next part, the big key word here is expected. So we know that's n times p for binomials, right? Let's take advantage of our shortcut. Our n is 500, our p is 18.1%, and hit enter. And we don't care if expected value or standard deviation is a decimal. That's just okay. That's our approximate center of our data. The only time you can't have those kind of decimals is for the usual range. As I already told you, expected value is the same thing as mean for binomials. In fact, it's true for any discrete distribution. It is not true for non-discrete, aka continuous distributions, which we'll learn about next week. But for discrete distributions, it's always true. Standard deviation, that's going to be the square root of n times p times q. And this is one of those cases where figuring out what that is, what the complement of 18.1% is hard, usually. So I'm going to say 1 minus 18.1%. Now, of course, if you can do that in your head, go for it. I'm not going to make a silly mistake, especially when I'm recording this for everybody. So I'm going to get the precise calculation with Excel. And so n was 500, p was 18.1, and q is just the complement of p. There we have it. So we want the range of values. We want the usual range. So we know what to do now. It's going to be our center, our mean, minus 2 times the deviation. We want our mean plus 2 times the deviation. But these are humans, these are objects, these are discrete things. So we would never witness these decimal calculations. And so let's actually be careful. So, little number line to help us out in visualizing everything. 73.28 is the smallest it can go. 107.72 is the biggest it can go. So what's the first number in our range that's acceptable? 74. Notice I'm not rounding the normal way. 107.72, this first number that's in our range that's acceptable is 107. Now, the one exception to this is if they tell you to round to the nearest whole number, then of course you round the normal way. You'd call that 73 and you'd call that 108. Typically, though, we want to stay within the usual range because the usual range officially starts at 73.2 and can't go any smaller. And so we would say 74. And it says the max you can go is 107.7. So the first object you could see is 107. But once in a while, I'll see an occasional homework question that doesn't actually want you to round by convention. And by convention, we go inwards within the range. And they'll say round to the nearest whole number. So just be mindful if it says round to the nearest whole number, then do it that way. You would call it 73 and 108. It's just slightly different numbers. Technically, 73 is too small and 108 is too big. So these are the values that you'd want to pick. And so if we get 500 people, anything from 74 to 107 of them would smoke. That would be normal, what we would expect. All right, let's go a lot faster now. Fixed trials, probability of success, and I'll leave it to you to verify that they're both conditions met, but essentially, yes, they're cracked, or no, they're not. So here we go. Binom.dis.range, 256 screens. The probability is 3%, and 5 or less. So the lowest it can be is 0, the biggest it can be is 5. And that's it. That's the probability that 5 or less is cracked. Okay, expected number. That means expected value, which for binomials is just n times p. 256 times 3%, and that's it. Standard deviation. Square root n times p times q, which is just a complement of p. There's our standard deviation. I'll even write it down just to remind us one more time. For binomials, it's NPQ. Okay. So now we're trying to find the probability that 16 or more is broken. Probability that we're trying to find 16 or more are broken. So let's see. Binom dot dis dot range. How many objects come in the box? 256. Probability is 3%. And 16 or more, 16 up to 256. 0.005. So now we want to know. I'll let you read the last question. Take it in for a second. I know it's going really fast there, so I'll be quiet for a second. Okay. So it says the company owner returns those screens for a refund, but he's angry that they had 16 of them cracked. And he claims that they're lying about this 3% stat. Does the answer using the concept of significance make sense? So remember, we look at extremes, and this is an extreme, right? We have 768 as our center. 16 is over here. So we're finding the probability being bigger. So that is definitely an extreme calculation, which we did. Is that calculation evidence of significance? Well, is that probability smaller than 0.05? And absolutely, because 0.05, 5 is bigger than 0, so yes. And so, yes, this is significant. Significant. I don't know why, that word always kind of trips me up. I think it's the extra I's. And it's actually written right there, I could just copy it, right? But yes, this is significant, which means that 16, because it's bigger than our expected value, 16 is unusually high. So we would not normally expect to get 16 broken glasses with a 3% broken rate. If that probability of success, the probability of a broken glass is only 3%, we would not expect to have 16 broken ones, which means one of two things. That 3% broken rate is a lie. And in fact, the company guy here is right in saying you lied about a 3% rate. Or he's just very unlucky and got a bad box. Because, this is not a zero probability. It is possible to get 16 broken glasses out of 256. It's just very, very, very unlikely, which means that either the company is lying or he's just very unlucky. And so the only way you would really know it is if you order another box. And if you order another box and you get, again, a lot of broken glasses, then you can say, no, I'm not working with you anymore. Clearly, you guys are not telling the truth about 3%. It's much higher than that. But if the next box is good, and the next box is good, and the next box is good, then he just had bad luck. So either they're lying about their 3% probability of success, a probability of broken glass, or he was just terribly unlucky and got a bad batch. Both of those possibilities are true, and you would need further evidence to kind of further investigate. And that further evidence we call hypothesis test, which you'll learn about for test 3. Okay, read this one and decide about the binomial distribution criteria. So do we have fixed trials? And are they discrete? Absolutely. It's just the total amount of frequencies, right? So if I add up all these frequencies, I do have fixed trials. It's met. There's my fixed trial, my N. Okay. Could I verify that they're independent? I have no evidence to show that they're not independent, so I would assume that each trial has the same chance or same number of outcomes. But where it fails at, you'll notice, is this question right here. What question were we researching? Is it a yes or no situation? If I ask you, how many pets do you own? And you say yes, I'm going to stare at you funny because it doesn't make sense. So in this case, it's not, it's not yes, no, which means that this is not binomial, which means all those fancy shortcuts we were using earlier, we can't use anymore. I know, sad face, because we got to do it the long way. So let's just scoot that over. And so we can't use the mean calculations. We can't do the mean and standard deviation the short way because we don't have a binomial situation, which means you got to do those ugly formulas. And it just is what it is. And so being able to identify that this is not binomial means we have to do manual calculations. So 37, whoops, let's click on it. It's a little faster. Let's click on the 37 divided by 150, right? With that frequency divided by the fixed trial, the total amount that won't change. Go back to it, drag it all the way to the right. We got our probabilities. And remember, for the mean, we're looking for x times p of x, and then we want to add them all up. So, writing my notes, x times p of x, take my calculation all the way to the right, and my mean, aka my expected value, is the sum of those calculations. At the mean now. And then we know our standard deviation is the square root of x minus the mean. I'm just going to call it x bar here for space, times p of x. And then we add those calculations up, and then lastly take the square root. So writing out our notes here so we know what we did, x minus the mean, and x minus the mean squared, and then x minus the mean squared times p of x, just building up the formula all the way down. Then we have our variance, then we have our standard deviation. And so we're going to do x minus mean, this x value, take away our mean. We don't want that mean to change, but it's not a nice number there, so we're going to put some dollar signs around the u. That tells Excel, don't change that calculation, but change the other one so we can drag it across. If you don't put the dollar signs around that cell reference of 1.493, it's not going to work. So we're going to lock our mean. And then, of course, we're going to square that calculation. Just clicked on it and made it to the power 2. And then we're going to take that squared value and times it by p of x. And then we're going to finally find the sum of that whole row once we get that row done. Finally, we can find the square root of our variance calculation. Of course, we're not done yet because I never did any dragging. I just wanted to get all the stuff in there. And if you ever see those hashtags, remember it's just too big of a number for the size of the box. And so you could, lengthen it out if you want to make it fit. But since honestly that row is not something I care about, I don't care if I see little hashtags in there. It's just saying it's a big number that it can't show me. All I really care about is these last two calculations anyways. So I'm going to highlight the first three that we need to drag across, go to my corner and drag them all the way down. And notice it did all my calculations. And yes, if I double click them, I can see what they actually were. I just don't care what these numbers are. They don't matter to me. All I care about is the variance and standard deviation. For this question, all you really care about is the standard deviation. And so there's my standard deviation and my mean. And of course, you can always do the one calculation drag, do the one calculation drag, one calculation drag. That's how I showed you last week. I like to do it a lot of times really fast. And since we're all used to it, I kind of did them all at once. I did one big drag all the way across. But there's your standard deviation. There's your mean. This is not binomial, so we couldn't use the fast shortcut. Then it says, use Excel to create a properly labeled formatted probability histogram. Because this one's a discrete distribution and not binomial, we would call it a discrete probability histogram.
And that just means they want a histogram of the relative frequency of the probability here. So we're going to highlight our probabilities, go to Insert and Bar Graph. There's our probabilities. And then we know the drill now. If you just click on it enough times, you can go to Quick Layout 8. If you're on a Mac, you'll have to find the Formatted Chart Series option and remove the gaps, all the same. And so we have a peak on the left, tail on the right, and so this is a right skewed distribution. And there we go. If you want to describe it, then of course you change your values, relative frequency. Down here, you would change this to your classes, your discrete values would start at 0, then 1, 2, all the usual stuff from the previous unit. Leave that part to you because that's just all the old-fashioned stuff. Okay, and that's it for this one. We already identified the shape, and we talked about other stuff. Let's keep it going. Okay. Identify the sample space. So let's see, we have beagles. So I'm going to do this little wiggly bracket to show sample space when you're making the list. And so we're going to have beagle 8 times. 3, 4, 5, 6, 7, 8. Labs 3 times. So 1, 2, 3. Golden retrievers, this is called them G's. So 1, 2, 3, 4. And this is why I like outcome space more than sample space, because you can just list out in the table format. These you actually got to write them all out. 1 poodle, so 1P, and 7 boxers. Because I already used B, I can't use B twice. So how about I call them X? So 1, 2, 3, 4, 5, 6, and 7. And that's my sample space. I just showed how everything could work out. If it was an outcome space, of course, we would just have a nice clean table, boxers, labs, blah, 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 and poodle, and then like that. And then you would just list out, there's 3 possibles, or I guess 8, and then 3, and 4. So the outcome space just shows in a nice table format, like we did the very first question of each of the possibilities. While a sample space, you list out every little bit, every little thing. Not a fan of this because this just takes too much time and I'm impatient. Anyways, if we select one dog, probability that it's a boxer. Well, if we make sure we check our binomial tricks, of course, we know that this is not binomial because we're not being asked about a yes or no situation. Or are we? Well, we are being asked about whether it's a boxer or not. So you could argue, yes, it's a boxer. No, it's not. But in this case, what's our fixed trial? Well, we're talking about one dog. So the fixed trial is 1. But what's our probability of success? Because the fixed trial is 1, the probability of success is just your standard probability. So this is technically doable with binomial, this particular question at least. It's just a lot of work to break this down. So in this kind of case, we're talking about an event of 1. It's generally easier just to go into the question and get your information. It's if you had like multiple dogs and that kind of stuff where it's more to your benefit. So in looking through here, we have boxers. We know there are 7 of them. So there's your numerator. And we just need to divide it by the total count. And let's just save us some time. 8 beagles, 3 labs, 4 golden retrievers, 1 poodle, and 7 boxers. So we have 23 total. And so it would be 7 out of 23. And there's our calculation. The reason why I'm hesitant to even try doing this by binomial methods is you'll notice that the probability of success changes for each question. You got a probability of a boxer, then probability of a lab or a beagle, and then other stuff. So you're not going to have the same probability of success. You have to go back and recalculate that over and over again. And it's just kind of pointless, honestly. So now we want to find the probability of labs or beagles. And of course, we should decide if labs or beagles are mutually exclusive because we see the word or. And based on this information up here, we're clearly separating labs from beagles, so there's no overlap. There's no dog that's both a lab and a beagle. When that happens, that means they are mutually exclusive because there's no overlap, and so it'll be the probability of one plus the probability of the other. And so the probability of a lab is 3 out of 23, and the probability of a beagle is 8 out of 23. Just add them up, hit go, and there's your answer. Okay. And of course, we're getting at the same concept in the very next question. Are they mutually exclusive? Is getting a boxer and a golden retriever exclusive to each other? Well, the probability, by the definition, means that we only have to show the probability of a boxer and golden retriever equals 0. That's the definition of mutually exclusive. And we can say this is true because we have 0 dogs that are both boxers and golden retrievers. Because there are 0 cases of that, it must be true. That's the whole point of it. Okay. Look at E. So I mentioned earlier, you could have done binomial for B and C because you are dealing with fixed trials, you are dealing with yes or no situations. It would just be a lot easier to do it that way. Think about E and whether or not you could do the binomial method. And the answer here is definitely not or no. You cannot use binomial, even if you wanted to. The previous ones you could, it's just a lot of extra work that you don't need to worry about. And this one you could not. And think about why. Well, in this case, she's getting a dog and you're getting a different dog. So what's going to happen when she picks her dog? There'll be one less dog for you. So initially, we have 24 dogs to choose from. And then the next time, there's only 23 when you go to pick your dog, or whoever picks first, it doesn't really matter. So this number is not independent. It's being changed by the first one, which we're getting at on the next question here, and we'll prove that in a second. But it's not binomial because the fixed trial is not staying the same. The first person gets 24 dog choices, the second one only gets 23. And since we know that, we could not use binomial even if we wanted to go through all that extra work. So she wants to select a dog, and we want them both to be boxers. So how many boxers are there? There were 7 boxers. I said 24. I meant 23 and 22. Sorry about that. And so there's 23 original dogs total. And then when the second person goes, there's only 22 left. And if there were 7 dogs originally, now there's only 6 of them are still boxers because, the first person kept their dog. We're not going to put it back, then what's the point of going to the pound in the first place, right? And so we're going to times these to get our solution. You have multiple probabilities, you multiply the probabilities. To find the multiple probabilities, you multiply the probabilities, yes. So 7 over 23 will times 6 over 22. There it is. That is our calculation. So the probability you both can go on there blind, or assuming you can't see the dogs, you just grab a random dog, and they both be boxers is 0.083. Obviously, if you're looking at the dogs, you can guarantee the probability of getting a boxer because you see them. We're assuming that you're just picking random dogs and you either don't know what they are or you don't actually see them. The probability they're boxers is 0.083. Okay. This is where I was getting the fact that the sister was getting the first dog. Are the events considered independent or dependent? So it's the probability that your sister gets a dog, in fact, a beagle, and then you go through a beagle. So your sister gets a dog, and then you get a dog. I guess I should call it Y, shouldn't I? I was thinking you like the letter. And then you get a dog. I said that backwards, right? Your sister gets a dog first. Probably that your sister got a dog, and then you get a dog. Are these things considered equal? Well, what's the probability that she would get a beagle? Well, there are 8 beagles out of 23 dogs. Well, if she got a beagle, how many beagles are left? There are 22. I'm sorry, there are 22 dogs. And how many beagles are left? There are 7. And so the question is, are these equal? If they're equal, then her choice is independent of your choice. It has no influence on it. Well, when she goes to pick a dog, she has a probability of blindly guessing 0.348 and getting a beagle. The probability you would get a beagle if she goes first is 0.318. These are not the same. So it's dependent. Her getting a beagle will impact your ability to get a beagle. In fact, it lowers your probability of getting a beagle. So her getting a beagle makes it harder for you to get a beagle. All right, last page, y'all. And it's just a continuation from that one question where I said last week, we will come back to this because it's binomial. And so reread part C here and see if you can pick out the elements of the formula. And then we'll do it and we'll be done for the day. Thank you for those who hung out with me the whole time. I know I went past my time. In this unit, I do that a fair amount just because it's a harder unit. Let's be honest. Okay, what's our fixed trial? Well, the total selection. What's our probability? We're talking about the probability of long-term care. 69% need long-term care. So there's our probability of success. It applies to all adults in the United States. And we're talking about adults. We're going to assume we're talking about the United States. Obviously, if it's a different country, it wouldn't work because we don't know the probability of adults in like China or France or England. We only know the probability for adults in the United States. So we're going to assume consistency, that they left that part off by accident. And then, of course, can we assume that each adult has the same possibility? We have to unless we see otherwise evidence. And what does yes and no mean? Yes means you need long-term care. No means you don't. So we have a yes or no situation. So we can use binomial stuff and think, gosh, because I don't want to do this calculation by hand. So what is the probability that 5 or less? So here we go. Dis.range. Our fixed trial was 100. 100. And we are looking for a probability of success of 69%. If you need long-term care, that was success. Then less than 5. So 0 going up to 4, right? Because 5 is not less than 5. 0 is less than 5, and 4 is less than 5. So that's our string. That's the minimum and maximum that's less than 5. Hit enter, and there's our calculation. It says it's 0, but let's add some decimals on here just to see if it really is 0. And eventually, way eventually, there it is. It's definitely not 0. It's, in fact, it's some weird number. Let's turn it to scientific notation to make it nice and easier. If I go to the general option, I can go down here to scientific. And you'll see it's 1.34 with 43 zeros out front. So in fact, if we're talking to 100 people, it is almost impossible to find that less than 5 will need care. It will be extremely unlikely that if you have a group of 500 adults over the age 65, that less than 5 of them will need some kind of care. Almost 0. Practically you can call it 0 because that's a lot of zeros involved. But there you go. That is the probability. 0.00042 times then 134. Now, in reality, what they're going to do on the homework and test questions, they're going to ask you to round that to the nearest hundredth or thousand, in which case you would call that zero because there's so many zeros involved. But that there is the precise calculation. All right, my friends, that is binomial distribution in a nutshell. Next week, I am doing normal distribution, and I'll be doing it either on Saturday or Tuesday of the following week. So this coming Tuesday is the same thing I just talked about. Then next week, I'll be doing normal distributions. Week after that, I'll be doing central limit theorem, then test prep, and then it's your test time.